Okay, well, everybody, welcome to the Financial Data Science Seminar, and I'm really happy to have Andreea Minca today, who is one of our own ORIE professors, and she will be talking about clustering heterogeneous financial networks. And I'm really excited about this topic specifically because, you know, I know that whenever we do financial engineering projects, we often end up wanting to cluster things or stocks or, you know, groups of customers, or, you know, clustering is sort of a recurrent theme in quantitative finance. And I'm really excited to see the kind of applications and theories that Andreea has been working on recently. So Andreea, welcome to the seminar, and the floor is yours.
All right, thank you so much, Sasha, and thank you for the invitation. It's really a pleasure to give the seminar, and it's really interesting because I've been at Cornell for quite some time, and I associate CFAM with working with practitioners, and I think this is yet another way to reach you guys. Indeed, so over the last decade, I've been working a lot on systemic risk and financial networks, and it was mostly from the modeling perspective. So how do nodes, how do banks, how do hedge funds, how do they connect to each other, and how can we represent this in terms of a network, and moreover trying to understand how you get a cumulative and it's going to be a highly nonlinear effect that comes from what happens at the level of a few nodes and then propagates to the entire network. And the work that I'm going to be presenting today is joined with Yudong Chen, who's one of our former colleagues, and with the student Xin Kan. And this was not so much on the modeling side, but rather on the algorithmic side. So that one was about, so this work is going deeper into the theory of clustering and developing algorithms that are adequate and that are more equipped to deal with the challenges that we have in financial networks. So now, the problem that we observed was that in general, I'm sure that this is what you observe also in practice, is that when you try to use clustering algorithms to detect financial network structures, they remain ad hoc. So it's generally off-the-shelf algorithms that are coming in general from either the networks science, and they've been developed with other applications in mind, and not necessarily developed with the financial network viewpoint. So we try to go one step forward in the direction of matching these algorithms to financial networks. And I'm going to be talking about two examples. So the first one is going to be about networks of overlapping portfolios, so that has application in portfolio selection. And second application is something that is more related to what I've been doing, and that is systemic risk analysis. And for that one, we are thinking about network of exposure. So exactly what I was saying, who is connected to whom, and exposure of one node to another node, and thinking really about this as an entire network, and trying to understand what is the level of risk in this network. Because if this network of exposures is going to have meaningful clusters, then essentially what this means is that each cluster is going to be vulnerable to the default or to illiquidity happening to one node or one institution in the cluster. So the larger the clusters, the larger the potential impact of distress of one member in that cluster. Whereas I think that for the network of overlapping portfolio, the application is twofold. So you could also think about it in terms of risk analysis, but more importantly, you could think about it in terms of how can I design, how can I do portfolio selection in a way that that avoids large clustering, or how can I do it in a way that that enhances diversification, and getting into this story of diversification, also the clustering viewpoint. So so yeah, the problem of clustering, of course, is not, as I said, is not specific to financial networks. This appears in all real-world networks. So nodes tend to form groups. So what is a cluster is such a group in which we observe that the connectivity within the group is larger than the connectivity between members of different groups. So we're going to say that the intra-group connectivity is larger than the intergroup connectivity. And in general, detecting clusters is challenging, and there are a lot of generic clustering algorithms out there, from the now classical modularity maximization. So this is it appeared in 2006 by Newman, and graph cut based models, and then likelihood-based methods, and probably what is familiar to many, spectral clustering and hierarchical clustering. So all this to say, there are a lot of algorithms out there, and each one is going to be adequate for different types of problems. So really the question is, why not take one of these existing algorithms off the shelf and apply them for financial networks? So there are several reasons. So an important reason is the heterogeneity. So financial networks have heterogeneity in terms of degrees. So the degrees exhibit what we call heavy tail distribution. So you're going to get that a very few number of the nodes have very high connectivity, and then most of them are having small connectivity, so small degrees. There is also heterogeneity in terms of weights. So if you think about these networks as being weighted networks, you are going to observe also a large heterogeneity in terms of weights, and you also observe that there is different intercommunity connectivity. So thinking about clusters perhaps as subsectors, you are going to have that each set of subsectors are going to have different inter and intra-connectivity. So you're not going to have so each one of the subsectors is going to behave in some sense differently. Now, another specific problem that makes it challenging to apply this off-the-shelf algorithm is the presence of outliers. So outliers, you cannot treat them as being one cluster by themselves. You can't say that okay, you have these sectors, and then each cluster is going to represent one sector, and then you have a bunch of outliers, and then we can think about them as a cluster in themselves. So you can't do that. They are going to appear, and for the purpose of the algorithm, they are going to behave as some adversaries, because they may have also the same connection patterns as inlier nodes, and at the same time they will so somebody tells me that they are still seeing the the title slide.
Yeah, we see the first slide. We thought it was a very big introduction, but you were showing us different slides.
Yes.
Okay.
So let me see. Okay. So I'm not sure why you're not seeing that.
Did you share your full screen or just the PowerPoint?
Application, the PowerPoint. Let me try again.
And it was not in presentation mode. It was in sort of, you know.
Oh, that's okay. So I will do. Let's try that then.
We see it now. We see it move.
Now you see it move. But how about now if I do a Control L? Okay, so that is not going to. L. Okay, so it's very interesting. Okay, so now you see it, right?
We see you move.
Yeah, now you can see. So I'm going to keep it like this because there seems to be my screen sharing is not really working as intended. So now you can see this move, right?
Yeah, we can see this.
Okay, so I was talking about these different challenges that you have when you cluster this type of networks. Yeah, I was talking about outliers. So these nodes, they don't belong to any clusters and they have arbitrary connection patterns. So for all practical purposes, they're going to behave as an adversary. And if you want an example, so thinking about financial networks and thinking about networks, let's say of banks, you could, or investment banks, you could think about a node like AIG Financial Products as an outlier because they were having many of their portfolios, derivatives portfolios, they were in essence like those of investment banks, but AIG Financial Products was of course not an investment bank, so it was part of a large insurer. So they tend to behave like one of the cluster nodes, but not in all respects. And moreover, they can be different in nature also among themselves. So as I said, you can't think about them as one cluster. And known algorithms such as spectral clustering are known to behave poorly in the presence of outliers. So if you have a data set and simply will apply spectral clustering, then even then it is not going to identify clusters. So it's the presence of outliers is going to hinder the performance of the algorithm, and many of the nodes are going to be misclassified. So that is one of the problems. So what we are going to base this work on is on a relaxation, semi-definite programming relaxation of the modularity maximization approach. And I'm going to be talking about that in a second. And now the clustering problem itself, it is an NP-hard combinatorial problem where you are trying to assign a group to each node in the network, and of course this is NP-hard. So in general, you have to search for all possible such attribution schemes. And now this is going to be relaxed to a semi-definite program that has tractable, that is going to have tractable algorithms. And of course, once you have this, what you want to do is prove that guarantee the quality of the clustering. So give certain conditions in terms of the tuning parameters that about the recovery of the true clusters. And of course, this problem have been solved in certain context before. So what we aim at is finding certain regularization that are going to solve the previous challenges. So deal with outliers, deal with heterogeneity, and deal with the different intra and intercluster probability of connection. So what we do is we introduce a novel regularization term that penalizes outliers with unusual connection patterns. So that's basically what you want to detect. You want to detect that you want to say, okay, this is an outlier, and you want to do that based on the connection pattern, and you want to say that that the way this outlier connects to the inlier is different than an inlier would connect to other inliers. So you want to say that essentially, even if the outlier has a large degree, it is going to behave differently than an inlier that is going to have similar degree, but perhaps is more central to their own cluster. And so right, and so this is work that is based on stochastic block model with outlier and on degree corrected stochastic block model by Tsai and Lia, respectively, Chen et al. And what we do is we provide theoretical guarantees for the exact recovery, and we don't make assumptions on the outlier nodes. So the only assumption that we are going to make on the outlier nodes is that we know their number, so we know the cardinality of the outlier node set. And we have explicit non-asymptotic condition for exact recovery. So the density gap, that this is going to be a condition on the difference between the intra and intercluster edge density. So of course the intra cluster edge density is going to be higher, assumed higher than the intercluster edge density. So we assume that there's more connectivity within the cluster than outside, than among nodes that are in two different clusters. This density must be larger than an expression that is based on natural problem parameters, such as the edge densities, the heterogeneity, the size of the cluster, and the number of inliers and outliers. And as what these algorithms are doing, and what these theorems and the guarantees are doing, are saying, look, let us, they're essentially existence theorems. They are saying there exists a range for the tuning parameters that make sense and that will guarantee the recovery of the clusters. And in terms of comparison with prior literature, the results that we have are more robust and contrary to previous works where the density gap conditions depend on both the n, the number of inliers, and m, so it's going to be a product of the number of inliers and number of outliers. Ours is going to be robust to the number of outliers, and it's only going to depend on the number of inliers. So no matter how many outlier nodes you have, these results are going to be robust. Of course, they will depend on the cardinality. Of course, the model itself will assume that we know the cardinality of the outlier set. So now, how we dealt with all of these things, and how are these models different than previous works. Now, the stochastic block model is perhaps the most well-known model of clustering, and it has, so usually it has homogeneous degrees for the inliers, and Now, in that particular case, a node, if you don't have outliers, then what will happen is that as soon as you see that, as soon as you observe that a node has an unusual degree, so it's unusual with respect to the typical degrees that you observe for the inliers, you can immediately say that this is going to be an outlier. Now, the problem that we have in financial networks is that you have this heterogeneity. So a node can have a very high or low degree simply because of the structure in the same of nodes in the same cluster. So you can't say that. So it could be that there's this heterogeneity, and this heterogeneity is normal for the cluster. So in banking systems, you observe the same thing. And I'm going to show you a banking system that is the Korean banking system, and in that one, you have that banks in the same sector and insurance companies that are also going to be same sector. They all exhibit this heterogeneity. So just because of the heterogeneity, they shouldn't be classified as outliers. So the algorithm should correctly identify these are banks and these are insurance companies and so on. And now, because of the degree distribution that is heavy-tailed, then we need to look not just at the degrees, but also the connectivity patterns. So who connects to whom? And this other thing is this other point is more of a technical point that in contrast to the previous work, we need to look at bounds not just in terms of the maximum degree, but rather look very carefully at the contributions to the bounds for each for nodes that have degrees in a certain range. And because of heterogeneity, we in contrast to previous work where there was a homogeneous penalization on diagonal terms, well, in this case, the adjacency matrix will the definiteness of the adjacency matrix will become worse, and then we need to make sure that the penalty terms that we introduce in our algorithms, they are going to account for the degree. So you cannot use the same homogeneous penalization for all nodes. So just let me dive into a bit of notation. So there isn't too much of notation. Let me see. Okay. All right. So a few questions. If there are any questions, I'm monitoring the chat. So please forward them as we go.
Yeah, this was just a small question about whether you would be sharing the slides, and I was announcing that we'd have the video, and maybe maybe you want to share the slides as well.
Yeah, sure. Yeah, so I think that's a good idea because there's a lot of notation to parse. So I'll do my best to go over that. So now, what are the fundamentals of this model? So we assume that we have a graph, and this is going to be the vertex set, and this is going to be the adjacency matrix. N is, as I said, the number of inliers, and M is the number of outliers. So in total, you have capital N vertices, and you assume that the number of, so this is something that we know. So we know the number of clusters. So you know that the inliers, they are partitioned into a bunch of unknown clusters. So C1, C2, CRs, and all this. So you know their number, but of course you don't know who belongs to which cluster. And you're going to observe an adjacency matrix. And the model is saying that, this is a primitive of the model. You're assuming that some heterogeneity parameters for each node. And in practice, these heterogeneity parameters, they could be, for example, the size of the portfolio. They could be an expected number of counterparties of a bank. So there would be a measure that is in the charge of the modeler. So that would be a measure of the heterogeneity. So this would be specified as you specify the model. And so, again, you also specify, so other than this heterogeneity parameter, now we are assuming that we also have some connectivity matrix of the class that is given at the level of the cluster. So now you're assuming that there is a basic connectivity matrix. They said, okay, on the basic level, a node from cluster A is going to be connected to a node in cluster B with a probability BAB. And now I'm going to adjust all of this and saying, okay, well, nodes, I'm going to adjust this by the heterogeneity parameter such that nodes that are more, and again, what does it mean? Have a higher theta means, or maybe they are larger if this theta represents size, or they are more connected if theta represents connectivity. So it's really these parameters beta, they can accommodate a lot of modeling choices.
So
now,
can I interrupt you for a quick question? Often in clustering, as you say, the off-the-shelf clustering methods, the output is often a pretty picture, and you look at it and you sometimes get insights, sometimes you don't. And here it seems that you have a very specific, more specific application or goal in mind related to these inliers and outliers. And I guess I'm wondering a little bit more how that fits, let's say, in the context of, the systemic risk, or, like the output beyond the nice picture is,
so that is a very good
AIG is a dangerous node or something like that, or
yes. So the output in clustering is going to be like, I'm going to show you a picture of that, and then you're going to observe the clusters. The problem is that those clusters, for certain in the present, when you have outlier nodes, so when you can assume that some nodes will not belong to any of these clusters, but may be apparent as a node in the cluster. Well, your pictures are going to be somewhat damaged by them. So in some sense, you need algorithms that make sure that in the presence of these outliers, they can still produce these pictures. And how do you assign? How do you define the algorithm? And I'm going to show you it's actually not very complex, but you do need to make certain adjustments to existing.
So the goal of these outliers is to fold them into a cluster, or is it more to sort of put a red alert and say,
exactly, to put a red alert, yes, to put a red alert and to not hinder the clustering itself. Because you could be mistakenly because they could hinder the classification of the inlier nodes. So now you are again assuming that in the basic model, so in there is this connectivity that comes from these parameters theta, and the connectivity is happening is adjusted by this heterogeneity parameter. So what you will observe is a realization of the network. So you'll observe a realization of the network. So for instance, somebody tells you, and I'll be showing you the Korean network. Somebody tells you, okay, this is a picture of the Korean network. Now go figure out which are the banks and which are the insurance companies, right? So and you're going to assume, okay, these are clusters, so they're more likely to be connected to each other. So so in the initial picture, in the initial network, if you want to call a network a picture, it's you are going to have the degree which is obtained from this adjacency matrix, and it looks a bit like this. So you're gonna make an assumption that the adjacency matrix can be written in this way, and here there would be the connectivity, so the adjacency matrix of the first cluster and the adjacency matrix of the R cluster, and this would be the adjacency matrix that correspond to the first outlier. outlier. And of course, your goal is to find this permutation matrix. So finding this permutation matrix that is going to tell you, okay, this particular node that you call, let's call it number one, well, this particular node number one is actually belonging to the cluster number one. And this particular node that is called number n is going to also belong to the first cluster. So it's really finding this permutation. So this is this unknown permutation matrix in which there is a single one in each row and column, and under this unknown permutation, the nodes are ordered according to the underlying structure of clusters and outliers. So other than this, you're assuming that there is this structure, and you're trying to find how do you map from the picture that you observe to this known structure, and this mapping is given by this permutation. And once you find this map, this permutation, then this permutation is going to tell you which node belongs to which cluster. So basically, for each candidate partition of the nodes, we can associate it, of course, with the partition matrix. And the details of that is that x, I, and j is going to be equal to 1 if and only if the nodes I and j are assigned to the same cluster. So here, if I'm going to put a all one matrix matrix that says, okay, all nodes in the first cluster, they are connected to each other, then this will correspond to the first cluster, and the second one is going to correspond to the second cluster, and this is going to be again an all one matrix, and so on. And here, these arbitrary entries, they will correspond to the outliers. So what you want to find, you want to find a partition that has this form, and this partition is going to implicitly give you this permutation as well. So this permutation again is the unknown permutation matrix that is going to in which the nodes are ordered according to the underlying structure of clusters and outliers. Okay, so now what is the algorithm doing? So the algorithm is based on, perhaps I can show you first, before I go into the details of these algorithms, maybe I will go and give you an example. So this example is the example of the Korean network, and what we observe in terms of the Korean network. This is data that that is published by Bank of Korea, and it is actually a snapshot of the entire financial ecosystem in Korea. And so you have a bunch of, so you have the banking system, insurance, and then you have securities, credit, specialized financial companies, asset management companies, mutual credit cooperative. And you have, you can think about it, it is not at the level of a network really, but you can map it to what I was saying in theory. So you can think about each one as being a cluster, and within each cluster you are going to have, of course, it's going to be 24 banks in the sample. And I think this mutual credit cooperative, there's 2,000 of them, and so some of them, some of the sectors contain lots of institutions, but looking at it and mapping to the model, you can say that there is a connectivity pattern that is observed here. So for example, you observe this connectivity pattern between insurance company and banks, and you observe here a connectivity pattern between security companies and banks, and so on. And this is not going to not everybody's connected to everybody else. So there's a weight over there, and you can think about this weight as the probability. So everything here is of course expressed in trillion wons, and you can think about it also in terms of probability of connection. The larger the flows in relation to the size of these sectors, the larger the probabilities of connection. So this would be somewhat, if you want. Oh, okay. So I didn't look very well. So you have here the number of institutions as well. So you have 17 banks, 56 insurance company, 56 securities, 93 asset management, credit finance, 86 and mutual finance, over 2000. And so for each one of them, in fact, you now. This is the snapshot of the connectivity of the sectors, and we will test the algorithms, and the goal of the algorithm is to recover and to identify correctly which one is a bank, which one is an insurance company, which one is a mutual finance company. And the way I test it is that I will create a network, and of course, in this case, since this is going to be a semi-synthetic network, I will know the ground truth. So I will know which is which, and then the algorithm has to correctly identify which is which. Now, how do I create the network? Well, from this you see that this is just at the level of the sector. So I will have to create also a connectivity pattern. These insurance companies, you see there are 56 of them, and this aggregate flow, it can be from any of the 56 insurance companies to any of the 17 banks. And on top of that, there is data that is also published by Bank of Korea on the size of assets, so assets and liabilities for all the financial institutions that you see over there. What is not published by Bank of Korea is the connection between each individual bank and another individual bank, or for that matter, between any financial institutions and any other financial institutions. So in other words, everything that is published is at aggregate level. So from this aggregate level, I'm going to recreate a network that represents connectivity at the level of the at institution level, and the heterogeneity parameter is going to be the size of the institution, and this is also something that is given in the data. So the algorithm is supposed to find these sectors from only one observation of the network. So kind of imagine that I'm feeding the algorithm a snapshot like this, but it's going to have more detail because it's going to have connectivity between any any insurance company and any bank. So it's going to be a much more detailed picture. And again, this is going to be a semi-synthetic network because it's going to be it's generated using another algorithm. So let me now go back to the algorithm itself. So now the algorithm itself is a variant of this modularity maximization, and the modularity is defined as the link density within clusters minus the expected link density. So this is what you observe. So this is part of the adjacency matrix. So again, I'm giving you the snapshot of the Korean network, and you're going to observe connectivity in that network. And you're going to be looking at the actual link density minus what would have been the expected link density if the edges were chosen randomly. And this is what you would be getting as a definition of modularity. And the more clustered the network is, the larger this modularity measure. Now, this quantity here, this represents the expected number of edges between two nodes. So if you took just two nodes at random, then this is what you'd observe. This is what you would have as expected number of edges between those two nodes. And of course, in your snapshot, in your picture, you're going to observe more or less than this. And so you the modularity maximization is going to attempt to recover which two nodes are in the same cluster based on this difference, a tuning parameter has been introduced. So instead of, people realize that instead of dealing with this expected number of edges, one can replace this with a tuning parameter, which gives you essentially a very, it gives you the following modularity maximization problem. Actually, here it's written, this difference is reversed, so it's becoming a minimization problem. And this constraint here, subject that X is a partition matrix, this is what makes this problem NP hard. So you essentially you'd have to search for all partition matrices, and then this is of course intractable. So and that is because of that particular constraint. So if you introduce a relaxation of the problem, you are no longer going to impose that this is a partition matrix. And remember, what was a partition matrix? A partition matrix was simply saying which nodes are going to be in the same cluster. So it's going to have one for an entry if those two nodes belong to the same cluster. And now you're in the relaxation, you are simply going to say that you're no longer going to impose this. So you're going to be saying that the entries are between 0 and 1. So essentially X is between 0, the matrix 0, and the all one matrix, and it's also positive semi-definite. And some technicalities here from this particular statement of the problem. You need to take care of this heterogeneity, and this is done by introducing this penalty terms. And now so what we are having here in terms of penalty, this is a penalty on the diagonal term, and this will what this will do is it's going to penalize a potential outlier whose degree is unusual, whose degree is beyond the normal variation that would be implied by a stochastic block model. And now you have a bunch of tuning parameters, so actually two tuning parameters here, and alpha controls the strength of this diagonal penalization. And importantly, this has to be done in accordance to the observed degree of the node. So and this is how you are going to determine which one are going to be the outliers and which ones are going to be the inliers. So if you see that node has high degree, and this term dominates, so this penalty dominates this difference, then it means that it does not have a strong community membership, but it simply has a large degree, and we can identify this safely as an outlier. On the other hand, you could be having that this term dominates this penalty term, and what this means is that the excess, so this term represents the excess or the difference between their community links. So this A represents the community links, and the difference between the community links and the expected community links. So if you have this difference, then those are the ones where you have a large number of of links within the same cluster, and then we can safely say that this have strong community membership.
Andreea, I have a question regarding the, so it comes from the Q&A. Are we talking about cross-sectional data for the Korean industry example?
Yeah,
or is there time series? They wanted to know if there was some time series component or. Yeah,
so there is no time series component. It's just a snapshot of the so there is no time series in this particular example. It is about a snapshot of the exposures in the Korean network as published by the Korean Central Bank. And so it's just a snapshot, and it says who is connected to who. It says, well, this is the total number of assets, total size of assets of each institution. And this is in fact given, so this is for each, it is reported the total number of assets for each institutions, but you don't know if those assets are because of a loan to another institution. So you just know it in aggregate. And you also know the exposures of each sector to another sector.
And but these exposures are just measured in the currency. So basically,
yes, won, right? They were in won, yeah.
Okay. And there's a direction, right? So
yes, and the direction is something that is also a snapshot that they published in the by the central bank.
Okay.
Yeah. So you see, like, and then like mapping that idea of the Korean network, this B, this is the connectivity matrix. So this is what gives you the probability of one sector being connected to another sector. And again, this is a modeler's job to say, how do I map from this picture that the Korean central bank gives me to my model? And then what we are saying is that B represents a connection probability. So when I see a big a strong weight on like here, a strong weight like here, I'm going to say that there is a large probability of connection between those two sectors. So imagine insurance is A, cluster A, and bank is cluster B. But so now I will skip all of this. So just to tell you what are the theoretical results. So the theoretical results, they are essentially intervals for the tuning parameter for this alpha and lambda that guarantee the perfect clustering. So these are, as I said, intervals. So it looks like this. They will depend on a bunch of the parameters of the model. So this is where you recognize the connectivity between clusters, and this is how you would be mapping to what you observe in data. The BAB would be, for example, in the Korean network, would be the probability of connection between, let's say, as I said, A insurance and B banks. And then if your lambda is in a right interval, then we are going to obtain clustering, and the clustering is via this matrix X that says which nodes. So it's going to have 1 if 2 nodes belong to the same cluster. So this one correctly recovers in this case the true cluster structure of the inliers. And of course, this is a statement that is non-asymptotic and is valid for a finite n. So in this case, I have to tell you that what is the probability of recovery. So the probability is of the form 1 minus O of 1 over n. So tends to 1 as with this speed as n becomes large. Okay, so now going back to this Korean network, now how we test our algorithm is from this picture that you have here. I am trying to recreate 20 sample networks that would be consistent with the aggregate values that we observe here, because the Korean central bank does not publish, of course, which insurance company is connected to which bank. So this is something that I have to generate in a synthetic network. And the aggregate values of assets and liabilities, they are given. And there is this algorithm that is in fact very useful, and many of the in many stress testing environments, this type of algorithms are used, because the central bank does not, or the regulator does not observe the entire network, and so you kind of have to fill in the gaps. So you have to use you have to use a method to fill in these gaps. And in this example, we use a Gibbs sampler to generate sample interbank liability matrices that are consistent with the aggregate value of assets and liabilities. So and this Korean sector example is a perfect setup, because we know the ground truth, we know the ground clustering, and we can test the performance of the algorithm via the misclassification rate, and we can see what it should have been assigned for a bank, and then is it assigned also, does the algorithm assign it correctly? So now, how the picture looks like. So if I am to generate one sample network with this starting from the global Korean picture, it is looking something like this. And you see, my picture is going to have here this bunch of this little cluster is going to be, I'm seeing it visually as a cluster. This is a cluster of banks. This is the insurance companies. I don't recall what this one are the mutual credit companies. And so you have this number of as many financial sectors. There's 6 of them, and there should be 6, 1, 2, 3, 4, 5, 6 on the diagonal, right? And so the algorithm is given this picture. And so the algorithm now has to say, well, these first guys here, they are the banks, and these other institutions over here, those are the insurance, and this one are the credit finance companies. So it's supposed to identify correctly to which sector they belong. And you see, visually, it's not entirely obvious that this set of institutions is not one cluster. It's actually 2 clusters. One of them is going to be the banks, and the other one, this small one is going to be the banks, and this one are going to be the insurance. And it's not obvious in the way you observe that it's actually a different type of institutions. You observe the connectivity pattern. So you observe the connectivity pattern that the banks are more connected to a bunch of other institutions, whereas these ones here, this other cluster here, those are the insurance, and they are not they don't have connections to this group over here. So let me look again. The third one is securities. So there wouldn't be connection between insurance and securities, but of course there would be connection between banks and security companies. So the algorithm has to be robust to all this heterogeneity in connectivity, and this is one of the performance criteria for the algorithm. So when you look at how this algorithm performs, you have to measure it in terms of misclassification rate. So we measure it in terms of other existing algorithms. So this would be the rate at which the algorithm misclassifies. So says, okay, credit company is a bank, and you see that this algorithm that I presented has the lowest misclassification rate. In general, I would say that misclassification rates tend to be on the low side for all of this algorithm, but for certain problems, the difference in algorithms can become significant. All right, and this core algorithm, which is based on spectral clustering, is the worst performer. I'm saying this because these are algorithms that are widely used in practice. So in the presence of this kind of challenges that I described for financial networks, this is one of the reasons why you wouldn't want to use off-the-shelf algorithms, and you want to look into more tweaking existing algorithms to account for all these issues that we encountered. And now the other, so I'm going to stop on this, the Korean network. I just want to take 1 minute or 2 minutes realistically on another application, which is something about that could have applications to investment portfolio management. Of course, I didn't look at the performance. I didn't test it out of sample, but that is something that could be considered. So let's say that you can look at funds, let's say mutual funds or hedge funds, or basically any institution that reports their holdings on the 13F in the 13F filings. Well, in this case, what you could do is you could recreate a network of overlapping portfolios. So you could measure the strengths of interaction between two institutions based on their portfolio holdings and how much this overlap. So you could do that. We described this in a bunch of papers, and it's not just our work. A lot of people have worked on this notion of overlapping portfolio. And so for our purposes, assume that you have a way to describe the portfolio structure via a network. And so now you want to say, well, let's look at this network. I'm giving you a snapshot. This is what you observe in terms of strengths. Now, I don't know the strategies of these funds. I don't know anything about them. All I know is what they have declared in the 13 filings. So, and from those ones, I can infer how strong are these connections and how overlapping those portfolios. And now let me do the what I've been describing. Let me now cluster these funds. Let me say, apply the clustering algorithm and say, okay, these funds are a big cluster. These other one are a big cluster. Well, the application of that would be you could achieve diversification by, let's say, allocate risk to each cluster. So, for example, if you were to invest in mutual funds, you would not invest. You do a cluster risk parity. In this case, you're going to account for the fact that a bunch of mutual funds, they are all in the same cluster, so they have huge overlap. So now this algorithm is going to tell how to cluster this network of overlapping portfolio. And now, of course, the algorithm is assuming that we tell how many clusters there are. So you can guess how let's say you assume that you have 5 clusters. And so when you do that, you can recover, the picture is going to look something like this, and it's going to recover 5 clusters, and then you 1, 2, 3, 4, 5, and you can then say, okay, and moreover, it's going to tell you which of the funds belongs to the first cluster, the second, the third, and so on. And so you can do that. I did it for the 2003 data, so connectivity of 2003 and versus 2012. So in each of these cases, it obtains a cluster, and what you observe is that from over this less like a decade, you observe that the bigger cluster becomes bigger. So that would indicate that there is more overlap in the portfolio. So of course, what remains to be seen is if you allocate your funds according to this, what would be the performance. But for our purposes, what we are providing is a tool with which to generate these clusters. And here it's a very interesting example, because if you compare this to existing clustering methods, what you okay, so I have a question for the Korean example. How does the algorithm decide the relationship between the specific companies based on just aggregated data from the government? How does the aggregated data get mapped to the more granular names. So as I was saying, this is done via an additional algorithm, which is not part of our work, that is doing exactly that. How it is filling in the gaps. It is creating individual networks that are consistent with the aggregate data from the government, and moreover, we can impose certain heterogeneity properties. Now, back to from the Korean, let's go back to this overlapping portfolios, and in the overlapping portfolios, I think that. So the clustering, other clusterings are less desirable because they observe, so this is what you would get into by using one of these two methods, so spectral clustering and Tsai-Lee. In spectral clustering, you would have high intercluster connectivity, and so Tsai-Lee would be this one, where so Tsai-Lee would be this one where you have one big and intra-connected cluster, and the other ones are barely connected. So then you wouldn't achieve anything in diversification, because you wouldn't know this here. It would be almost uninformative. They would be completely like almost unconnected among each other. So it wouldn't be really looking like you'd expect for a cluster, and there would be one huge cluster, which would be undesirable from a diversification standpoint. Whereas this other one that is you'd have spectral clustering, and that one would have one cluster which has extremely high intercluster connectivity, and then connection, and then here you'd have on the other extreme, you have one cluster that has basically no connectivity, no intercluster, and no very low intracluster connectivity as well. So in general, both of this wouldn't achieve diversification. And as opposed to looking at this picture over here, where you get somewhat 5 alternatives where you could diversify under a cluster risk parity approach. All right, so thank you all. So if we have, that's all I wanted to say. So thanks again for the questions, and if there are more questions, I'd be happy to quickly take more of them.
While we wait for some questions to come in, I have a little one that I wanted to ask you. So many of these clustering algorithms, I think including yours, has as an input the number n, the number of clusters. And
the number R is the number of clusters. Yeah.
R, okay. So what I think was really interesting in your work with the Korean networks is that there was an imposed R by the structure. You knew that there were 6 groups, and then you tested your clustering algorithm by seeing, oh, how well do I fit into those groups? Or I think
actually in that one as well, we are also, we said we knew that there were 6 sectors, so we knew the number of clusters.
Yeah. So you knew 6, you knew the number 6, but then after you used the number 6, you were able to say, oh, we misclassified, or you were able to quantify how well the algorithm did. And I wonder if in the other application, the portfolio one, at the end of the day, these mutual funds often have styles like growth, mid cap, large cap, value. They also have natural names, and I wonder whether there's some potential to use that, the number of categories as the number 7. We need 7.
Exactly, and this is what we did. So from that one, we used exactly the usual types of investment as number of categories, and this is what you would do. But then it would be very interesting to see if this completely data-driven approach, where you just look at the holdings and you'd get a cluster, if that actual cluster is matching the investment category that the fund declares. So that would be something also interesting. to see, or if they are overlapping across investment strategies. And also at the end of the day, it depends. So it would be now, what do you really care about in practice? Do you care about actual holdings, or do you care about their target strategy? Because de facto they will have some overlapping portfolios, and these are the ones that are going to determine the impact, price impacts, and so on. So probably you want to assess whether the recover clustering using this data-driven approach are matching the target strategy, and then you'd want to take into account both of them.
Okay, well, we have some questions.
We have a bunch of questions. One about the preprint. Yes, the preprint exists and it's posted publicly. And
is the title the same as the title of your talk, so people can Google
it?
Yes.
And you can search it on my website as well. You mentioned a tool. Is that something that's available? It's not publicly available, the tool. It would be a simple implementation of the algorithm using standard tools in optimization. And a lot of algorithms are sensitive to the number of cluster. Is this the same case for the new algorithm? I think so. Yes, I think that indeed the algorithm depends on the number of clusters. Now what you would, yes, so you would ask yourself, are the, let's say that I'm considering a clustering algorithm, and I'm assuming that I'm having 5 investment strategies, and then I'm going to be recovering 5 clusters, and then assuming that I'm going to say next that the algorithm takes 6 clusters, you'd want to see a certain relationship between the two. So I cannot say whether this, how the clustering under 2 different choices are going to compare. So we don't have theoretical results on this, and so this would imply that you'd have to have very good domain knowledge about the number of clusters, or make a very good standing assumption about this number of clusters.
Okay, Andrea, well, it looks like we've answered all the questions, and we had a lot of interesting feedback and questions today. So I really enjoyed your talk, and thanks.
Right, thank you. All right, good evening, everybody. Bye.